Apologies in advance for any rogue purring that you hear in this video. Sprocket was assisting me with the voice mixing this time. Hello Internet, my name is Quinn and this is Blondihacks. Today I'm going to finish the mechanical hand pump that lives inside the water tender on my Pennsylvania A3 switcher. This is the backup pump. The main locomotive pump is an axle pump underneath the engine, but this one is for secondary use and also pressure testing the boiler, various other utility functions. We'll find out today if this thing can move water or not. So let's go. Let's start simple with this little brass plug that goes into the top of the valve body to seal it. I've got this piece of scrap round bar that should do the job. I'm going to start here in the mill by putting a large hexagonal profile on the end of the stock. The final piece does have a hex profile at the top, but not nearly this big, of course. The point of this, though, is that it will give me a way to hold it in the 3-jaw chuck conveniently in my lathe, and then when I'm done, I'll have just enough of the hex profile left at the top that the final part requires. I've got a bunch of excess stock, so I'll just Yahtzee that off the end to save myself some time. Face off the end to clean up the parting cut, as is tradition. And now I can get down to the turn-in. There's a very thin diameter at the very bottom. This is sort of a peg that holds the ball spring in place inside the valve body. Once I've got that dimension set, then I turn a larger diameter above that, and this will be for the thread that actually goes into the plug area and holds it in place. Above that is a 45-degree taper that blends into the hex profile. This is not decorative, this is actually a sealing surface. And because it's 45 degrees and this is brass, I can get away with using my chamfering tool as a form tool and do this cut in one easy step. This taper seats down against a sharp 90-degree corner in the valve body, and that's actually all that's required to seal it. It's a pretty clever design. Similar to the internals of a cone-style union fitting that you would use on pipework, this requires no gasket or O-ring or anything to seal. Finally, the threads go on there, and this piece is basically done. It's time for the parting blade. And Yahtzee. Here's the final piece after a little bit of deburring and cleanup, and I'm pretty pleased with that. Looks like the drawing anyway. Next up is the cone-shaped pickup for the underside of the pump. This is where the water comes into the pump, and this is very similar to the piece we just did, but I need to start with a much larger piece of stock because it has this big cone shape on the bottom of it. Similar to the plug on the top, it gets a thread turned into the bottom of it, above which lies the same 45-degree sealing taper that the plug had. Things get a little different from here, though. Of course, we need a hole down the middle of it because this is the water intake, not just a plug. That's an easy drilling operation. Now I can do the large cone diameter that's at the very top of this piece, which forms the inverted funnel. I'm going to try and do this with my chamfer tool all in one cut. This is brass, so I think I can get away with this. This is going to be a very heavy form cut, even for brass, but if I go slow, and as I got closer to the end, I had to go slower and slower to keep it from chattering, as you would expect, but I did get away with this. Thank goodness for free machining brass. That saved me having to set up my compound for a lot of single point cutting passes for cutting that taper. In the last video in this series, you may recall that we used this specially ground valve seat cutting tool. We need to do that again, but I'm not going to do it in the tailstock this time because the tailstock isn't going to line up the cutter very well with the edge in this situation. So instead, I'm going to put that cutter in my tool post, and that will allow me to align it a little bit more to the side. But the 15-degree angle that we need to cut for the valve seat is the same as we did in the valve body. And just like in the valve body, it creates a fragile peak that we can then crush with a ball bearing later to create the seal. While I still have this excess stock on it, I'm going to take it over to the mill, and I'm going to put it in my hex collet block, and I'm going to cut the wrench profile that's required between the sealing taper and the big funnel shape. For once, I actually did a good job of thinking through the order of operations on this part. Then we go back over to the lathe, and I'm putting it in, not that way, the other way. I'm going to hold it by just the very edge of the large diameter where the end of the funnel is going to end up. And that will allow me to turn down this excess stock and create the interior of that funnel shape. Now I've actually got a fair bit of run out here because I'm holding just the edge of the stock with an ER collet. ER collets do not like doing this. They really need to be holding the stock most of the length down the collet. However, you can get away with this a little bit, especially if you're doing easy cuts like in brass, but honestly, not really recommended. This isn't great for the collet, but well, do what I say, not what I do. This is a use case where 5C collets are really a better choice because they can grip with full force right at the front edge of the collet without hurting anything. However, I don't have a 5C collet chuck for my lathe, so I may do with this. After facing to length, I go in with a drill and just create a little bit of a cone, and that's going to give me a starting point for my boring bar. I'm going to single point cut the inside of this funnel now, and it was helpful to give the boring bar a little bit of place to start cutting. From here, it's a pretty straightforward single point taper turning operation with the compound. I'm feeding out with the cross slide after each pass, and then feeding in with the compound using the boring bar. Fortunately, the cutter on the head of this boring bar is just small enough that I can make this cut. There's just enough clearance at the bottom of that cone that I can get in there. Bit of a test of skill to chamfer that with the file without scratching up my collet, but got away with that, and here is the final pickup. The lathe work is all done. This is a really neat part. It's a little bit over-designed, honestly, for what it's doing, but yeah, it's really cool looking. Now to create the valve seat, this is done the same way as we did in the valve body if you watched that video. Put the ball bearing on there. The special drift that we made for this purpose goes on top of that. A little light tappy tap tap. And that's all it takes. Blow test is successful, so we've got a good valve seat. Here's a close look at that, which I couldn't show you before. You can see this kind of shiny ring around the top of the hole. That's the little curved interface that the ball bearing created by crushing the 15-degree point that was on there. Pretty neat. There are other ways that people do that, but this is a traditional method in model engineering for making check valves. Finally, a brass screen is soft soldered to the underside of the pickup to act as a bit of a filter. A finer mesh than this would be better, but I had this stuff on hand and I didn't want to order something. It has to be brass so that you can soft solder it, because any kind of screener mesh is going to be destroyed by the heat of silver soldering. The functional value of this mesh is pretty dubious. There aren't going to be any large rocks or birds in the water tank, but it's a neat detail. Time for the piston now. I've got this 316 stainless round bar. It's precision ground, and we start by putting a point on the end of the piston. This being 316 stainless, I am definitely not getting away with a form tool this time. So single point taper turning with the compound it is. After the point is cut, then I can pull it out to final length and part this thing off. And then I realized it's probably a suicide mission to try parting off 316 stainless in this lathe, so I took it out and took it over to the bandsaw, cut it over length, and then put it back in the lathe and faced it down to final length. I had to put it back in the lathe anyway because we need to put a chamfer on the back of it. A chamfer on the back, which I can do with a form tool because it's a small one, will help the piston move smoothly in the bore, and of course separates us from the animals. Over to the mill now for the slot feature at the end. We need a cross hole first of all, so that's easy to do in the collet block. This holds the pin that actually drives the piston forward and back at the end of the handle. Next, we need a slot 90 degrees from that pin feature, and that's easy to do with the collet block, hence this setup. I'm going to use a method for cutting this slot suggested by Kozo. It's not one that I've done before, but being that this is 316 stainless, I think it'll be a good choice. The way he suggests doing this is by drilling another cross hole. This cross hole is actually a little bit oversized, so it gives kind of a balloon shape to the end of the slot, which I think helps with clearance for the mechanism. Then once you've drilled that cross hole, then I turn it back 90 degrees again, thanks to the collet block, and I go in with the slitting saw, and I cut up to the center line of that hole above and below. This was a maximum pucker operation for me because I have never used a slitting saw in 316 stainless, and slitting saws are terrifying at the best of times. I gotta say though, this worked really well. Not in a hurry, 250 RPM, nice gentle feed, lots of lubricant, and it cruised right through there. Then a second cut at the bottom side of the hole completes the slot. Normally I would do a slot like this with an end mill, but being 3/16 stainless, it would have required a lot of passes and a lot of light cuts. So I think this drilling and slitting method actually was a better way to go in this case. At least it would have been if I had done the math right on the quill DRO. As you can see, the second cut is actually not in the right place. It's a little bit too far in, so my slot is too small by quite a bit, as you can see on that gauge block, and it's a little bit offside. But conveniently the error was in my favor, so I was able to correct it with some filing. And by filing, I mean the Dremel tool, because filing 3/16 stainless is for jumps. Then I cleaned up the Dremel marks with a file until I had a perfect fit on that gauge block. Look at that. Beautiful. Here's the completed piston. The slot is not the prettiest thing in the world due to the amount of handwork that I had to do at the end there, but it'll certainly be functional. Not bad for a rookie in 3/16 stainless. While I have that stuff out, I'm going to make the pump handle. That's a long piece of 3/16 stainless. The only interesting feature really is that it needs a ball end on it. It's really not worth getting out the ball turning tool for a single aesthetic feature like this, so I'm going to step turn it instead. And in fact, I'm just going to eyeball it. I'm not doing any measurements here. All that time I spent in the 80s doing pixel art for video games has trained me for this moment. I know how to make a curve approximation from square shoulders. Once I'm kind of close with the step turning, then I can finish up with filing it to the radius gauge that I have. Then the filing marks get cleaned up with some emery paper. Final check with the radius gauge, and good enough. The purpose of that feature is just so the pump handle feels comfortable in your hand and also looks nice. Over to the mill. Now this handle needs a deep slot in it, very similar to the piston, but I don't have a slitting saw big enough to do it this time, so I can't use the same method. So instead I am going to mill it, but I'm going to start by chain drilling this out, because again, milling this much 3/16 stainless with a tiny end mill like this is an exercise in pain. After chain drilling it, then I just have a little bit of material to clean up with the end mill, and that went reasonably quickly. I still did a lot of light cuts because I didn't want to push my luck. This is a small end mill, and I've got a lot of stick out. My setup isn't especially rigid, so I didn't want to push my luck on any of the machining variables here. There's no sense in being in a hurry. I've got time. This is a hobby. I can check the fit of that slot using the bar stock from which the piece that fits in here will be made, and that is a good fit. It's not, unfortunately, again, a very pretty slot. The mistake I made this time was the chain drill size that I used was a little bit oversized. I mean, it was on size. Really, you need to go smaller because the drills tend to deflect a little bit when they're drilling, and then the end mill, when it's doing its cuts, doesn't have enough material to remove to fully clean up the drill marks. But that slot is going to be fully inside this collar that I'm now making, so no one will ever see it anyway. And this is 303 stainless that I have in a larger diameter, so this is much easier going. I drilled a great big hole down the center of this, and then I'm going to ream it because it needs to be a really close fit around the pump handle that we just made. This collar is going to go around the slotted end, and it's going to form kind of an enclosure that will lock into the lever arm of the pump. That's a really nice fit in there, so we're done with this step. This time I will use the Yatsifier because this is 303 stainless, which cuts very easily. It's a little bit tougher than mild steel, but still easy to machine. A little bit of Loctite will hold that collar on there for good. And you can see the final shape that creates on the end. This is a quick release handle, basically, that's going to be able to go on and off the pump as needed. It's a nice design. I like it a lot. Next up is the lever arm that goes in that pump handle. I've got this 303 flat bar from which I'll rough cut a piece, and then I'm going to go over to the mill and machine the edges nice and parallel. The reason is, even though the final piece actually does not have parallel sides, I need to be able to hold this thing for a bunch of operations before we cut the tapered shape in it. Now let's look at that pump handle again. You see the shape formed by that collar and that slot? It's not actually a square tang that needs to go in there. It needs to be a tang with rounded sides for a perfect fit. That's really interesting. So I'm going to create that over here on the lathe by putting the end of the flat bar sticking out of the four-jaw chuck like this. Then I dial that in so it's concentric, just like any rectangular stock. I did do a video on this on four-jaw chuck techniques if you want to know how this is done. This is a little bit trickier than usual because of the thin edges, but still not too difficult to get this thing dialed in. Then I turn a diameter on the end of this tang the same diameter as the pump handle. And then it will slide inside that collar that we put on the end of the pump handle, and it'll be a perfect tang with rounded sides to fit into that slot that we created. Now you could certainly argue that this is overkill. Just making a square-sided tang would probably work fine, but this doesn't take very long to do, and it does ensure a really nice secure fit on the handle, which makes sure that it isn't sloppy while you're using the pump, which could be really annoying. I turned it to the point where I could feel that it almost wanted to go in. Like it's starting to go. I could probably force it on, but I don't want to force it on. I might not be able to remove it, but I'm kind of like within Scotch-Brite wheel range at this point, so I don't want to take another cut. I decided to leave it here, and I put it on the Scotch-Brite wheel and did a little bit of handwork with emery paper to really dial in a perfect fit. So now that fits on there really nicely. It's easy to slide on and off, but when it's on there, there's zero play in it. Really nice kind of friction push fit. And well, I'd be lying if I said I didn't just sit here doing this for quite a while, because this is why I like machining. While the sides of this are still parallel and it's easy to hold, I'm going to put it in the vise and I'm going to put the two holes in it for the pins, the two pivot pins that make this into a functional lever. The spacing of these holes is of course very important so that the stroke of the pump is correct and the angle of the handle at each end of the stroke is correct. That will matter at the end, as you'll see. So these get drilled and reamed. Finally, this needs to be tapered to match the drawing. This is partly aesthetic, but also does serve some function. It increases the clearance of this lever on the associated linkages, as you'll see. I just did this with layout, and I line up the layout line with a parallel on top of my vise jaw, then remove the parallel, mill down to the line, and we'll have a good taper. The accuracy of this taper is not so critical that anything more than milling to a layout line is required. Then to round the end, I install my end rounding fixture on the belt sander using Robertson screws, the finest of screws. If you watch my videos a lot, you may have seen me build this fixture recently for my belt sander. It's a really quick and easy way to round the ends of things when it only is primarily aesthetic and doesn't have to be a micron accurate radius. There's the final pump lever arm. I think that came out really nice. Honestly, this really couldn't have gone better except for the fact that I made it 1/8 of an inch too short and got to make it again. The final length of this part is actually pretty important, as you'll see in the final operation of the pump. Next up is this brass top link that connects the top of the lever to the top of the pump. I had to mill down some stock to the right OD. This gets a couple of those pinholes drilled in it once again for all of the various linkages. And then this needs slots in the ends as well, very similar to the end of the piston. So for that, I rotate it sideways and drill that out and use the slitting saw once again, just like we did on the piston. This method is slower than just using an end mill, especially in brass, but it does give you that bulbous end on the slot with the slightly oversized drill that Kozo specifies in the drawings. Again, I assume for clearance. Once again then to the belt sander to round the ends of those. There's the final linkage there. Very pleased with that. That really went perfectly, except for the fact that I missed the detail that one of the slots is actually supposed to be deeper than the other one, so rather than messing with slitting saws again, I just threw an end mill in there and plowed out the excess. All these various linkages and things are connected with little tiny pins. This is 1/8 inch 3/16 stainless round bar. I'm going to face off the end, and I'm going to need to put a bunch of tiny snap ring grooves in it. Actually, these are E-clip grooves to be specific. For this, I ground a grooving tool just 20 thousandths wide, the smallest tool I've ever ground actually. I'm working very close to the chuck because we're going to need the most rigidity we can get. This is such small diameter stock, and we're trying to use a grooving tool, which is always a lot of tool pressure, and this is 3/16 stainless, so all of the variables working against us here. But working very close to the chuck, low speed, lots of lubricant, and that actually seemed to go okay. I special ordered stainless steel E-clips for this purpose. All of these parts are going to be forever submerged in water, so everything needs to be stainless or brass or bronze. And that is a perfect fit on there. Very, very nice. Now to do the second one at the other end, I'm pulling it out and leaving it in the chuck, and then lining up on the previous slot with my grooving tool and doing my translation down from there to get the spacing correct. This way I'm always working close to the chuck. I could also part it off and flip it over, but then it's much more difficult to get the spacing correct on the grooves because the other groove that you just cut is inside the chuck somewhere. At this point, I'm ready to part it off, and I was feeling lucky, so I thought, you know what, let's try the parting blade this time. And that actually worked, it parted it off, but look at the slow-mo afterwards. See how the end of the stock is flopping around. So the force of the parting tool actually bent the stock. So while the parting was successful, it ruined the end of that stock. And I ended up doing the rest of them with a fret saw so that I didn't have to lop a bent chunk off of the stock each time. Okay, we're ready for a test assembly. Let's see if the mechanism moves smoothly. This bronze bushing is the O-ring retainer. I made that off camera, wasn't very exciting. That goes in there, piston goes in there. The top link attaches to the fulcrum like so. Then the pump handle goes in the piston and into the top link like so. And then finally the pump handle goes on that lever arm. It certainly looks the part. The motion is a bit stiff, but that's typical for mechanisms like this. If you build all of your parts to really close tolerances, the resulting mechanism always needs a bit of running in before it works smoothly. So that doesn't concern me. What does concern me is that I'm not getting the stroke out of this pump that I'm supposed to. The drawing specifies 3/4 inches of stroke, and I'm only getting about 1/3 of that. So there's definitely some clearancing needed here somewhere. And somewhere is in fact the slot on the piston and a little bit of the slot on the top link probably as well. Those are hitting. So I did some filing and I managed to improve that situation. In my defense, however, in the first drawing of this piston, it shows a small slot. In the second drawing of this piston, it shows a much deeper slot. That is not an accident. Kozo doesn't make mistakes like that in his drawings, so that's clearly intentional. And there's a cryptic note in the drawing that says, "File after assembly." However, there's no mention of this at all in the build notes or the instructions in the book, so pretty sure though that he expects you to need to clearance these slots. That did the trick though, a little bit of filing, and now I've got right on 3/4 of an inch of stroke like it's supposed to have, so I feel good about that. There's another issue here though with this O-ring retainer. It's held in place by this single set screw, and as you can see, it's really not doing a very good job. If I tighten that screw down further, then it compresses that thin-walled bushing, and now the piston doesn't move very well, and it still isn't really retaining it, as you can see. So this whole design, honestly, just isn't very good. I would probably like to see some small screws going into the face of this flange to hold it in place, but let's see if I can do a smaller change that will still fix it. There's enough wall thickness on this bushing that I think I can put a dimple in there, which will create a mechanical lock on that set screw instead of relying on the friction of a tiny brass screw. So I put a little dimple in that with a drill in a pin vise, and I also put a little bit of a point on the end of the set screw to hold it in place, and then the set screw will be installed with Loctite to make sure that it doesn't back out. The tension needs to be just so that it's sitting in that dimple without compressing the bushing, and then Loctite will make sure it stays there. That seems to be working well. It's retaining its position now and the piston moves freely, so I think we succeeded, but I won't be surprised if I have to revisit that. If you noticed that hole in the end of the pump body and wondered what it's for, there's a screw that gets threaded in there to hold the lower check valve ball in place. And that gets Loctited in as well, so it's not a leak. For the upper check valve, it has a spring to help hold it in place. You're supposed to make that spring, but I forgot to order the special diameter wire that Kozo specifies. I found a spring in my drawer that should work close enough for now, but I am going to make that spring later. And then the plug goes down in there to seal that and hold the ball in place. Then the other ball goes on the lower intake valve. That valve does not need a spring on it because the pressure of the pump holds it in place. All right, let's give this thing a test. Let's see if it shifts water. Got it set up immersed in a water tank. Because of the design of the pickup of this thing, it's very large and quite tall, so the whole pickup has to be immersed in water or this pump isn't going to work. Honestly, a tube lying in the bottom of the tank would actually probably be more effective, but hey, I'm not here to question the design. Well, actually, I guess that's literally what I'm doing. But let's see if it works as designed. There's going to be a little bit of foam and air at first until the pump primes. These piston pumps are always like that. But once the air is flushed out and it's primed, magic happens. The pump gets quiet and it just starts shifting nothing but water on every single stroke. And it's really, really cool. It doesn't move a lot of water on every stroke, but I mean, this is a 3/8 bore and 3/4 inch stroke, so that's what you're going to get. And this is a small locomotive, it doesn't need much. I think that's really neat. All right, let's get this thing installed, or at least temporarily installed, in its final location so you can see how it's going to work. It bolts onto a bolt pattern in the floor of the tender that we had already done previously, way back in the beginning of this tender build. Remember those days? Ah, simpler times. Then the tank is going to sit down on top of it, and you'll notice something cool about that pump lever. Look at where it lands. This is the coolest feature of this pump. You just open the water hatch. There's the pump arm right there. Pump handle goes on that, and Kozo has designed it so that the stroke of this pump perfectly fits in the opening for the water hatch. And you can use the pump without ever needing to open anything or get inside the tender at all. And then when you're done, handle comes off, close the hatch, and it's like it was never there. It's a secret pump. It's a very nice little design for this pump. It does exactly what it needs to in the small space that it has available. As I said earlier, I would probably revisit the design of that pickup. I think it's a little bit overly fussy and it's sitting too high up to really make maximum use of the contents of the water tank, but honestly, for a locomotive like this, it's going to be just fine, I'm sure. We still need to pressure test this pump to make sure it can handle the 200 psi of boiler pressure, but that's not usually an issue. These pumps usually just work in that regard, but I'll be checking that after we've done all of the plumbing that gets attached to it. Well, thank you very much for watching. Thanks to my patrons for making all of this content possible, and I will see you next time.